So let's begin. Yeah, so this is the basic outline of the presentation. Before I start with the outline of the presentation, let me give you a brief context of the issue that I am trying to deal with. Actually, if you see Mumbai High offshore oil field, India's biggest oil field, it is said to be in the mature stage of production. So what do you mean by the mature stage? That its oil production is declining and water production is increasing. If you see any oil and gas field in the initial years, its oil production is increasing, its oil production is in the build-up stage. Then you have a peak stage. Then the oil production plateaus and then it begins to decline. This is the mature stage of production. So Mumbai High is also in the mature stage of production. Oil production is declining and water production is increasing. Right now, the average water cut of Mumbai High is 80%. It produces around 6 lakh barrels per day of liquid, and out of that, 80% is water. So that is a huge amount of water that we are getting. So now this water is actually of no use to us. It is a nuisance because we have to treat it before disposing it off. So this adds to the cost of production. So here my study comes into play that how you can generate electricity using this produced water from oil and gas wells. So firstly, we'll see the technology, that how this will be done. Next, the prospect, how much electricity can be generated in the Mumbai High offshore oil field. And thirdly, the proof. We'll discuss worldwide projects where this technology has already been applied in the oil fields. So next. So firstly, the technology, the electricity, how it can be generated. So if I answer you in one word, the technology is using an organic Rankine cycle power plant. So what it is, I'll be telling. So firstly, if you've seen conventional geothermal applications, the pressure and temperature of the reservoir, the subsurface is such that in the reservoir we have steam. When we drill a well, at the surface only we get steam. Now this steam can be directly used to rotate a turbine and generate electricity. But in all the cases, we don't get steam at the surface. Sometimes the pressure and temperature at the surface is such that the steam condenses into water. So we are getting water and the temperature of the water is still high, let's say around 90 to 95 degrees Celsius. So in this case, what is done is that we use an organic Rankine cycle power plant. Now what happens is in this plant is that firstly the hot water enters the plant. The first step, there is a heat exchanger. In the heat exchanger, the heat energy of the water is extracted and transferred to a secondary fluid. Now this is called the working fluid. The working fluid is a low boiling point refrigerant or an organic fluid like a hydrocarbon N-pentane with a boiling point of, let's say, around 15 to 20 degrees Celsius. So the heat energy of the water is extracted, given to the working fluid. This working fluid evaporates and this vapor is used to drive the turbine. And then the vapors are condensed and then it is pumped back to the heat exchanger and this cycle continues. So my idea was that when such type of technology is used in conventional geothermal wells, why can't we apply it in the oil field? Because in the oil field also we have huge amount of water, we have the flow rate, we have the temperatures, so we can use the same technology in oil field also. So we'll be seeing how much electricity can be generated. So next. So this figure you are seeing, this is a heat exchanger, a plate and type heat exchanger. The two fluids, hot and cold fluids, are coming in contact with each other and the temperature is exchanging. So yeah, this is a schematic of the organic Rankine cycle power plant. On the left you have one with a water-cooled condenser, and on the right you have one with the air-cooled condenser. So you can have different condensing strategies to cool the vapors of the working fluid and then convert it into liquid and continue the cycle. So these are the specifications of an organic Rankine cycle plant which was developed by a company called Electratherm and used in an oil field in USA. So you can see the refrigerant, the working fluid that they were using was R25FA. This is pentafluoropropane with a boiling point of 15 degrees Celsius. And the expander, the turbine, had efficiency of 75%, the generator had efficiency of 91%, and the system efficiency was 6 to 10%. All these efficiencies are important to incorporate when we need to calculate that from the amount of thermal energy that we extract from the water, how much can be converted into electric power. So yeah, this is a schematic of how the plant can be incorporated in an oil field. Like from the subsurface formation, your fluids come up, the oil and gas water is separated, the water is treated, and then it enters the ORC plant. And after all the processes that go inside the plant, it is re-injected into the formation. So if you don't install the plant, water will directly be re-injected into the formation after the treatment. So this is a photo of an actual ORC plant installed in one of the oil fields in France, in the Chonnoy oil field. We'll be talking about this in few further slides. So yeah, now the interesting part, that how much electricity can be generated using this technology in Mumbai High offshore oil field. Yeah, so just to give you a brief idea about the Mumbai High oil field, it is an offshore oil field. The formation is carbonate or limestone, and it is located at a distance of 200 kilometers from Mumbai shore, that is Juhu beach you can say, at a water depth of around 70 to 100 meter. So Mumbai High oil field has 6 different process complexes. Now this is a process complex. There are 6 such process complexes in Mumbai High field. In this process complex, what happens is that oil and gas, which is collected from the wells, is processed. The oil, water, gas is separated, water is treated, and then all these processes are carried. The oil is sent to the refinery or further for processing. So we have 6 such process complexes in Mumbai High field. So what we can do is, let's say we install an organic Rankine cycle plant in all these 6 process complexes. So in this table here, you can see complex wise amount of water that is produced in all these process complexes. Let's say the process complex 1, it produces around 1,51,000 barrels of water per day. So this is a huge quantity of water that is being produced in all these process complexes. And the average temperature that we have found of the produced water after separation is around 65 to 75 degrees Celsius. So we have good temperature, we have huge amount of flow rate, and if we incorporate a ORC plant in all these process complexes, we can generate substantial amount of electricity. And this electricity is not only emission free, this can also, in normal cases, we generate electricity in process complex using a turbine generator, TG, which uses the natural gas from the oil wells. So we can supplement electricity using this technology, and we can save the natural gas also, which can be sold and we can generate revenue. Plus the electricity would be emission free. It will also reduce your greenhouse gas emissions. So yeah, so here is the temperature and flow rate data. The surface temperature is around 65 to 75 degrees Celsius. The flow rate at different process complexes are given in the table. And now we'll see how we can calculate the amount of electric power that is possible. Yeah, so electric power output calculation is done using 2 methods. In method 1, using the general thermodynamics, see the equation Q equal to mc delta T. It gives you the amount of thermal energy that is stored in the water and that is released into the ORC plant. Let's say the water enters the ORC plant at T1 temperature and it exits at TO. So Q equal to mc dt, we get the amount of thermal energy that was released by the water as input to the ORC plant. And now the ORC plant would use this much amount of thermal energy as input, and based on its efficiency will convert it into electric power. So if we multiply this by the efficiency, we get the electric power that is generated. Now the efficiencies that we saw earlier, the different components are like the turbine efficiency, the electric generator efficiency, and the net cycle thermal efficiency. So the turbine efficiency and generator efficiency we have used, which was earlier given in the table itself. But the net cycle thermal efficiency, we can calculate using 3 different correlations. 3 different papers have given 3 different correlations using which we can calculate this thermal efficiency. So you can see all the correlations given here. So we have calculated the efficiency at 3 different temperatures, and we have used the correlation which gave the least amount of efficiency to calculate the electric power. That was by MIT 2006 study. So yeah, just a calculation showing the electric power. So let's say we install a ORC power plant in process complex 1.
Mudit, may I request you to make it a little bit faster? As I see, still there are around 17 slides and we have only 5 more minutes.
So in process complex 1, we can see the flow rate, the inlet temperature, the outlet temperature. Inlet temperature was 75, outlet was 45, and we have the specific heat capacity. So by Q equal to mc dt, we got the thermal energy, we converted into thermal power, and then for electric power, we had three different efficiencies, we multiplied that. So in process complex 1, we could generate 1.12 megawatt of electricity using this technology. So similarly, we have calculated the power output possible in all the different process complexes. And this is method 2. In method 2, we have a graph given by MIT 2006 study. On the x-axis, you have the inlet temperature. So if you know the inlet temperature, you have your outlet temperature. On y-axis, you get the power output per unit of flow rate. So you can multiply it by your flow rate and get the power output. So yeah, here we can see the electricity potential calculated for all the 6 different process complexes using the method 2. And here we have compared all the methods, method 1 and method 2. You can see the results are almost similar. Like in process complex 1, by method 1, we can see the electric power that is coming is 1.12 megawatt. And by method 2, it is 1.02 megawatt. So that is a substantial amount of electricity. So the proof, the worldwide projects, now we'll see. See, the first example is about 2009 Rocky Mountain Oilfield Testing Center. This power plant was installed in USA in the Teapot Dome oil field in 2009. The flow rate input that they had was around 12,000 barrels per day of water at inlet temperature of 90 to 92. Outlet temperature they got was 30 to 77. And the amount of electricity that they could generate using this water from oil and gas field was 80 to 280 kilowatt. This is the photograph of the ORC plant that they employed in the USA Teapot Dome oil field. The next example that we have is Denbury Summerland 2 well. This well was also in Mississippi state of USA. The ORC plant was manufactured by the company Electratherm. The flow rate was around 4,000 barrels per day and inlet water temperature of 95, and they used the working fluid R25FA, pentafluoropropane, which is the most commonly used working fluid, boiling point of 15, and the output power of the plant was 19 to 22. This is the photograph of the plant. And this is the graph showing the electric power output, how it varies in the entire day. So you can see the red line, as the ambient temperature goes up, the electric power output goes down because your outlet temperature increases. So next is the example of China. This is in the Hubei oil field operated by PetroChina. The plant was installed in 2012. The flow rate that they have was around 18,000 barrels per day of water at an inlet water temperature of 110. Outlet water temperature was 85 to 90. And they could generate around 360 kilowatt of electricity there. These are the photographs of the ORC power plant in China. Next is the example of 2 oil fields in Colombia. It was mentioned in the paper as OFA and OFB, oil fields A and B. They were situated in the central eastern part of Colombia, and there the flow water input was around 40,000 for oil field A and 15,000 barrels per day for oil field B, and the inlet water temperature was around 100 degrees Celsius for oil field A and 88 degrees Celsius for oil field B. And the output power that they could generate was around 180 to 200 kilowatt and 50 to 70 kilowatt for oil field B. So you can see developing countries like Colombia also have used this technology, so why not India? And this is a photograph of the ORC plants used in Colombia and the graph of electric power generated with how it varies with the ambient environment temperature. So now last is the example of the Chenoy oil field in France. The plant was installed in around 2021. The flow rate input that they had was around 3,100 barrels per day because they installed the plant only for 2-3 wells, so the flow rate was very less. Inlet water temperature 90 to 95, outlet water temperature 80 to 85, and they could generate around 10 to 20 kilowatt of electricity. This value is very less because the flow rate is also very less here, around 3,000 barrels per day only. So this is the photograph of the ORC plant in France, installed in the Chenoy oil field in France, 20 kilowatt electric. So thank you for being patient listening.
Thanks, Mudit, for a nice presentation. Mainly Mudit explained how geothermal energy can be used to produce electricity. He explained the methodology of ORC cycle through which how the electricity can be generated, and also provided a couple of methods how we can calculate the amount of power that can be generated through the ORC method. And finally, he concluded some of the practical live examples where this geothermal energy has been in production for producing the electricity. Thank you. Now I invite Parikshit Gupta from HPCL to provide his presentation on energy efficient design for combined cycle power plant and carbon capture.
Good evening, everyone. It is an honor for me to stand here in this large forum of Indian Energy Week, which brings all energy leaders, innovators, and experts shaping the future of energy sector. India's energy sector is at a very pivotal moment, balancing growth, sustainability, and technological advancement. We are also in a position to have environmental sustainability and challenges like power generation, which is a big concern in India. As India, we are aiming for net zero emission by 2070, where we still have coal to be remain as major source for power demand. And in my presentation, I would like to tell you about that we are having a combined cycle power plant, which is nowadays it is implemented in over worldwide. The main reason why there's a constraint with having combined cycle power plant in higher temperature areas is the inlet air. As due to high inlet air temperature, the high compressor work is required to drive the turbine. And the second most important parameters that we have in our power plants is CO2 emissions. Right now in India, we have 0.5 kg of CO2 per kilowatt hour. That's the current CO2 emissions from a captive power plant. As India, the overall rise in global temperatures keeps below 2 degrees centigrade, there will be an irreversible climate change will occur. As this picture states, the picture of Muir Glacier in 1941 and the picture of Muir Glacier in 2004, it is very evident that there is a severe devastating effect of climate change. Now we would be directly focusing on our model. We have gas turbine, steam turbine, which is combined to make a combined cycle power plant. Usually in gas turbine, we have, in combined cycle power plant, we have gas turbine as a topping cycle and steam turbine as a bottoming cycle. So these are the parameters being used for our study. Whereas for gas turbines, we have used 53 megawatts, and for steam turbines, we have used 30 megawatts. And for both these turbines, we are using to cool the inlet air of the gas turbine using vapor absorption refrigerant cycle, which is consuming around 6.2 megawatts of power. That is self-driven by the steam turbine. We have 3 case studies based on our design. That is combined cycle power plant without VARS. That's a normal combined cycle power plant. The other is combined cycle power plant with VARS. The third one is combined cycle power plant with VARS and CCS. This is a novel approach called carbon capture system, which we have tried to put in our system. Now, basic operations of combined cycle power plant. This is a steam turbine, that's the bottoming cycle. And this is a gas turbine, that's a topping cycle. This is a limitation which we are talking about in the previous slide, that the high temperature of the inlet air is responsible for high compressor work. As we have higher temperatures in the western part of Rajasthan, that is Barmer, in the month of May, the average daily temperature is 42 degrees centigrade, which probably this plant is probably very efficient over there. Now we would like to show the subsystem of our proposed model. This is the VRS cycle, which will be implanted on the upstream of gas turbine to cooling the inlet air. This is the pictorial diagram of combined carbon capture system. Now, this is the model which we have integrated with VRS carbon capture system in our combined cycle power plant. This is the steam turbine. This is the topping cycle of gas turbine. This is vapor absorption refrigeration cycle. And this is our carbon capture system. So whole sums up to our model. Next, the objective of our proposed model. What we are trying to do from this model is the cooling the inlet air in a gas cycle using absorption chiller. Second, the possibility of below dew point temperature to condensate water from the moist air. We are also getting moist air by the cooling the inlet air of the gas turbine. We are optimize the power output of gas turbine and steam turbine, and the carbon capture is carried out in this model. So getting back to our case one, we have case one where we have only combined cycle power plant without anything. That's the normal combined cycle power plant, which has given us a power of output of 77 megawatts, which has gas turbine giving us 47 megawatts and steam turbine giving 29.87 megawatts. In this model, we got results of CO2 emissions as 0.459 kg of CO2 per kilowatt hour of power generation. That's in a hot climate of May. The efficiency of this power plant in the May was 45.5 degrees centigrade, and in January it was 47.37 megawatts. And in this case too, we have our combined cycle power plant with vapor absorption reference cycle. We have our in-house generator, which is driven by the steam from the steam turbine. So in this case, as the steam blade we have increased, so we have dropped down the inlet air temperature and the compressor work. So in this case, the power output was 77 megawatts, and the individual power from steam and gas turbine is 28 megawatts and 52.93 megawatts. And the combined power output was found to be 82 megawatts. Now there is a change in power output. Due to the steam which we have bled from the steam turbine, there's a drop of work from steam turbine. And there's a significant increase in work from the gas turbine as we have dropped down the inlet air of the gas turbine. As we can see, there's for 8% of steam bleed, we have dropped down the power of 1.05 megawatts from steam turbines, and significantly we have increased the gas turbine output by 5.74 megawatts. And as I've told earlier, that the condensed water is also available due to the cooling of inlet air. So in our study, we got around 2.66 cubic meter of water per hour. That's 0.74 kg per second from our VRS cycle. It can also be utilized in our utilities and our subsystems where it is where water is there's a scarcity of water in the areas. In case 3, we have CO2 emissions of CCPP with CCS. This is the third case where we have VRS and combined carbon capture system along with combined cycle power plant. The CO2 emissions are significantly reduced to 1.048 kg per second, and the carbon capture efficiency is found out to be 89.17 percentage. Whereas it is very evident that the carbon capture system is very energy intensive, as it has consumed around 23.84 megawatts of energy. Now the power output from the third system was found to be 57.917 megawatts. There's a drop of power output which has been observed due to the energy consumed by our carbon capture system. That is 23.84 megawatts of energy has been consumed by our carbon capture system. So the overall power output has dropped to 57.917 megawatts. So, and in similar case, the efficiency of the complete system has dropped to in a range of 34 to 31 degrees centigrade, 31%. Now, I would like to conclude it like the whole 3 models with our existing power plant. That's the primary goal of our study. In our steam turbine, where we don't have gas turbines, we have 30% of efficiency. When we have installed our VRS cycle, we have got around 45.5% of efficiency. And in the third case, where we have put in VRS, we have got 48.27% of increase in efficiency. Close to 3% of increase in efficiency has been observed in our VRS system. And in the case, the last case where we have a combined cycle power plant with the carbon capture, we have dropped the efficiency to 34.20, which was mainly due to the power consumption by combined cycle carbon capture system. Now, this is the CO2 emissions which we have calculated, and the power output was the amount of CO2 emissions was found to be 0.7 kg per kilowatt hour of power generation in the normal steam turbine. When we have put in the VRS cycle, the efficiency, the carbon emissions was dropped to 0.459 kg per kilowatt hours. And in our third system, where we have VRS cycle, we have got around 0.422 kg per kilowatt hours of carbon emissions. In the third case, where we have put in our carbon capture system, it can be seen very evidently that the CO2 emissions has dropped very significantly to 0.0645 kg per kilowatt hours. So this is a very sustainable system where we can have a VRS cycle carbon capture system where the power output can also be increased and the environmental norms can also be met in the system. So the country is prioritizing the sustainable energy and preservation the environmental protection. The adoption of inlet air cooling is an imperative at this current juncture. The proposed model yields a tangible quantitative results which has been shown, and costing has not yet taken into picture, but the results are very positive, which shows the drop in carbon emissions and rise in power output. Thank you for the time, and I look forward for engaging an insightful discussion. Thank you.
Thanks, Parikshit, for the nice presentation. Mainly, Parikshit explained the energy efficient design of the combined cycle power plant, where he explained 3 scenarios: CCPP without VARs, and with VARs, and with CCS. And he showcased how the results will vary, how the power output can be increased, and how carbon emission can be reduced. Thank you. Now I would like to invite Bikram Prasad to provide his presentation on effective chemical formulation for solar panel cleaning.
Good afternoon, everyone. Good afternoon, everyone. I am Bikram Prasad, Chief Manager R&D Products Commercialization, placed in Mumbai, HPCL. Herein we are going to discuss about effective chemical formulation for solar panel chemical cleaning. So we have developed a product called HP Solaro Care. So now our presentation will comprise of 5 parts. One would be business case, another would be functional features and lab studies. Thereafter, field trial, what we have conducted, and the conclusions, what we could gather from those, all the aspects. Now, business case. Solar panel chemical cleaning is increasing day by day or year on year. By the year 2020, in year 2020, it was $1.1 billion market, and we expect that by 2027, it will be a $1.9 billion market with a CAGR of 9.9%. Now, when we talk about solar panels are primarily hindered. The power conversion efficiency got hindered by the dust particles. This is the accumulation of dust particles is the major reason of decrease in power conversion efficiency. There are other factors as well, like pollen, bird droppings, sea salt, dirt, etc. So on and so forth. And we can attribute certain of these reasons to geography of the place. When you talk about the decrease in power conversion efficiency due to dust, it goes as high as 50% over a period of time. However, when we say that month on month, on an average, the decrease in power conversion efficiency is to the extent of 13%. Now, how big Indian market is when we talk about globally? India stands at fourth rank with 6.6% market share of solar panel power generation through solar panels. So we are, I mean, with this we can conclude that it is very much necessary to have solar panel cleaning liquids. Now, how does it work? How the solar panel chemical cleaning will work? See, traditionally the chemicals are consisting of surfactants having hydrophilic and hydrophobic heads. The hydrophilic heads can normally gets deposited on the dirt side, and gradually the head of the hydrophilic will attract all the hydrophilics and the dust particles accumulated, and it will form a micelle. The formation of the micelle is the main criteria of this surfactant part. Now, when we talk about commercial chemicals, there are several. During our R&D part, research part, we observed that there are several active components which are there in the commercial solar panel cleaning liquid, which we try to address in our HP Solaro Care. In active components, there are surfactants like non-ionic surfactants, which are, although good interaction having dust deposits, it will remove dust deposits. However, it is having poor cleaning ability in hard deposits. Now, we try to improve upon that by having cationic and anionic components, which will lead to less to hard soil deposits removal. There are chelating agents also. These chelating agents are primarily having hypochlorite salts in traditional commercial solar panel chemicals, which is having better dissolving capacity when we talk about carbonate deposits. However, these are highly corrosive in nature. We observed this and we tried to get rid of this by having no hypochlorite salts in our chelating agents. We observed that there are medium to strong acids also available in the traditional cleaning, which is having these acids will lead to removal of hard scales and microbial stains also. But these are having that potentiality to damage the panels of the solar panels. We try to overcome it by having active cleaning and antimicrobial agents in our formulation. Now, what is the novelty in our chemical? Our chemical comprises of compatibility of anionic and cationic surfactants having antimicrobial and selective chelating agents, as we observed that there was no hypochlorite salts there. It is having lesser dosage, and it is having we have observed that there is no corrosion feature in our chemical. And it is having better antimicrobial properties as compared to other traditional solar panel cleaning liquids. It is having a better cleaning efficiency and having a suitable pH, a better pH as compared to other liquids. It is highly active against the dust-containing metals, including sodium, aluminum, silicon, iron, potassium, and calcium. Now, herein we see that we tried to formulate more than 15 chemicals. We worked on that, and we found that there are several aspects which we have to cater to when we are formulating that chemical. We have to see that our pH has to be a better one. We have to see that it does not precipitate and it does not give any settlements on the panels. We have to see that it is working on several kinds of dust particles and pollen grains like that, and it is non-corrosive. On top of that, it is having that antimicrobial property also. So herein we can see that the first one, the SR01 is our HP Solaro Care, and it is having a pH of 6.5. The efficiency, when we say efficiency, herein we will say that there is an efficiency comparison between benchmark, which is the commercial chemical, the water, and HP Solaro Care. HP Solaro Care has led to an improvement in PCE, power conversion efficiency, by 0.8 kilowatt per hour. But it is, in terms of efficiency, it is 3.61% more efficient. However, the water was only 1.04 and the traditional chemical was at 3.08. I would also like to inform you that most of the traditional chemical cleanings does not have any properties which gives antimicrobial things. See, these solar panels are up in the nature. These are exposed to climate. So there is a very high tendency of getting fungus or bacteria settling on the solar panels. Over a period of time, it will lead to decrease in the PCE. we improved upon that. We have formulated in such a way that our chemical, our HP Solar Care addresses all those issues of antimicrobials. We found that it is working on most of the bacterial and fungal antimicrobials, microorganisms. Corrosion test, we did the corrosion test and we found that HP Solar Care, there is no pitting which is being observed. In commercial chemical there is a pitting observed, and you will see the corrosion rate which is there. Corrosion rate is 0.67 millimeter per year. However, in case of commercial chemical, it is to the extent of 8.6 millimeter per year. And there is no pitting observed in HP Solar Care. Percentage efficiency, we have done field trial, extensive field trial have been done, not only in HPCL, however outside HPCL as well. On an average, if I'll give you the ballpark number, this is the value addition in HP Solar Care versus water. We are improving by 10%, and in case of HP Solar Care versus traditional chemical, we are better by 3.7%. We have done, this is the number of which has been done on 2 megawatt in our HP GRDC plant. There is a 10% improvement observed over a 3 months period time. We have done commercialization of this particular chemical. We have served to outside HPCL as well. In HPCL, we have given to several units of ours, including refinery, HPCL Vizag refinery, terminals. Outside HPCL, we have given to our PMHMBL and then MRPL and ACME as well. These are the performance certificates which has been obtained. So you will see that in one of the performance certificates, there is a number given by 9.6% improvement over water and 3.7% improvement over traditional chemical. Now I will also give you one piece of information that this is the percentage of improvement of 1 year only, right? When we go year on year basis, the antimicrobial thing or the settlement of microorganisms, the corrosive thing of the chemical hampers the solar panel a lot. So those things cannot be captured here. This is an interesting data points which we have captured. In our VRMP Vizag refinery modern plant, we have done it. And in a month-on-month basis, you will see that there is an improvement of more than 4,30,000 when we compare it from March to April month. You will see that the kilowatt has improved from 92 to 93 kilowatt in 1 month, giving a potential benefit of 4 lakh rupees. Now the benefits are, as I explained, that the benefits are cost effective. This is definitely a cost effective when we compare it with the commercial available chemical. It has definitely got a market potential, and we are happy to say that it is all indigenously obtained chemicals that we are doing this. So obviously it is towards that Atmanirbhar Bharat theme. We have obtained patents from India as well as US. Advantages are cost effective, it is highly efficient, it is having good antimicrobial property, and it is less corrosive in nature. Thank you so much. Thank you so much for giving the time and opportunity.
Thanks, Vikram Prasad, for the nice presentation. He explained how solar work care can be used to improve the efficiency of the solar panels. As you all know, solar panels faces the problem of soiling losses because of dust or pollen or climate environmental changes. So this is where instead of cleaning the solar panels using ordinary chemicals, solar work care can be more effective in generating more power output from the existing solar panels. Thank you. With that, I conclude this session. Thank you for participating in this session.